So, you've probably used an AI like ChatGPT. We all have. But have you ever really wondered what's going on under the hood? Like, how are these incredibly complex things actually built? Today, we're going to pull back the curtain and take a look. And it brings up this kind of weird paradox, right? AI is easier to use than ever before. You can just call an API, type in a prompt, and boom, you get these amazing results. So why on earth are the top experts at places like Stanford going back to square one, insisting on building these things completely from scratch? That's the big question we're tackling today. Well, the answer really gets at the heart of a huge problem in AI research right now, the black box issue. As these tools get simpler on the surface, our real understanding of what's happening inside is actually shrinking. And listen to this. Percy Lang from Stanford puts it perfectly. He says, we're facing a real crisis where researchers who used to build their own models are now just users of someone else's giant proprietary system. And yeah, that's powerful for sure, but it creates this massive gap between using AI and truly understanding it. The term for this is a leaky abstraction. It's a fancy way of saying we know what goes in and we know what comes out, but the why and the how in the middle are a mystery. We don't have that gut feeling for where it might break or why it makes certain choices. And if you want to do real fundamental research, you can't just be a user. You've got to be able to get in there and tear the whole thing apart. Okay, so if the answer is build it to understand it, then why doesn't everybody just, build their own? Well, the answer comes down to one word: scale. The sheer size of these things creates what is essentially a giant wall. Let's just try to wrap our heads around this for a second. A model like GPT-4 is rumored to have something like 1.8 trillion parameters. That's 1.8 trillion little knobs and dials that the AI tunes during training. I mean, it's a number that basically just breaks your brain. And the price tag? Oh boy. To train a model at that scale, we're talking about an estimated $100 million for one training run. This isn't a weekend project in your garage. We're talking about a level of investment that's usually reserved for governments. So right about now, you're probably thinking, okay, fine, I can't build the giant one. I'll just build a little baby version to practice on. Great idea, right? Well, here's the kicker. Small models are not just mini versions of the big ones. They behave in completely different ways. Just look at this chart. It tells the whole story. See, in a small model, the computer's effort is split pretty much 50-50 between two key parts, the attention part and the MLP part. But when you scale that model way, way up, whoa, the MLP part just takes over. It's more than 90% of the work. So if you spend all your time optimizing the attention part on your tiny model, you'd be solving the completely wrong problem for the big one. And then you get to this wild idea called emergent behaviors. This is where things get really weird. These are skills that a model just suddenly develops once it gets big enough. They're not there at all in the smaller versions. Like, a small model can't do math. But you cross a certain threshold of size, and bam, it can do arithmetic. The same thing happens with writing code. It means you can't ever really predict what a model will be able to do until you actually build it at that massive scale. So we're kind of in a tough spot, right? The biggest models are way out of reach, and the small ones don't tell you the whole story. So what's the point? Why bother building from scratch at all? This really brings us to the core reason for doing this. The answer is so simple, but it's also incredibly profound. Look, the goal isn't to compete with GPT-4 in your garage. The goal is to learn. It's in the actual doing, the building, the debugging, the optimizing. That's where the real, deep, valuable understanding comes from. So what are you actually learning? Well, it really boils down to three big things. First, you get the mechanics, the nuts and bolts, the raw ingredients of how these things work. Second, you develop the mindset. You learn to think about efficiency and scale in a whole new way. And maybe most important, you build the intuitions, that gut feeling for what kind of data and what design choices actually make a model sing. Okay, so let's say you're on board with the why, but what about the how? Where would you even start? Well, you can actually break down this huge, intimidating process into a pretty clear set of steps. First up are the basics, writing the actual code for the model and the part that lets it read, the tokenizer. Then comes systems, which is all about making that code run ridiculously fast. It's like tuning the engine on a Formula One car. After that, you have data. I mean, a model is useless without fuel, right? And this is where you collect and clean just mountains of text. And finally, you get to alignment. This is where you take that raw, powerful model and you shape it. You fine-tune it to be helpful and safe, using techniques like RLHF. I know, that whole pipeline can still feel a little up in the clouds. So let's get our hands dirty. Let's zoom way, way in on the very first piece of the puzzle. To make this real, tokens. Before an AI can write poetry or code, it has to learn how to read. And that process is called tokenization. Really, all it is a way to take a sentence, chop it up into little pieces called tokens, and then turn each piece into a number. Because, let's be honest, a neural network doesn't speak English. It speaks math, so you have to translate for it. But how you chop it up, that's the tricky part. The obvious ideas don't really work. If you break it down into individual letters or bytes, your sentences become super long, and that's just horribly inefficient for the model to process. But if you use whole words, your vocabulary gets gigantic, and you have no idea what to do with new words or even typos. So what do? Well, this is where the genius comes in. It's an algorithm called byte pair encoding, or BPE. And this thing is the perfect example of why you build from scratch. Instead of us telling it the rules, BPE is a super clever algorithm that actually learns the best way to chop up text by looking at the data itself. And the way it works is it's beautiful. It's so simple. You start with everything broken down into individual letters or bytes. The algorithm scans through and finds the pair that shows up most often, like maybe T and H. It then merges them into a new token, teach. Then it does it again. Maybe the next most common pair is I and N, so it creates an in token. And you just repeat that process thousands and thousands of times, and it organically builds the perfect, most efficient vocabulary for your data. Okay, so this all brings us to a really important final point. There's this famous idea in AI called the bitter lesson, and a lot of people get it wrong. They think it just means bigger is better, that you can solve anything by just throwing more computers at it. But that's not the real insight. The real lesson is that it's about algorithms at scale. It's not about brute force. It's about being smart. It's about efficiency. Because if you can make your code just a tiny bit more efficient when you're running a $100 million training job, that tiny bit saves you millions of dollars and gets you a way better model. The name of the game is squeezing every last drop of performance out of the hardware you've got. So at the end of the day, building from scratch completely reframes the challenge. The question is no longer just who has the most money to build the biggest thing. The much more interesting and frankly more important question for the future of innovation is this. Given a fixed budget, a set amount of computing power and data, what is the absolute best, most efficient, most capable model that you can possibly build? Answering that question, that's how we're really going to invent what's next in AI.